All right, so hi, and thanks for joining my talk, Breaking the Attack Graph. I'm Irina Simakov, and I'm a security researcher at Microsoft in the ATA/Azure ATP group. And today I want to talk to you about how defenders can leverage graphs in order to create a more secure domain environment. So let's see our agenda for this talk. I'll begin with discussing a few attack tools today that use graphs and graph theory, such as Bloodhound and GoFetch, and then we'll see how defenders can be using graphs for different security purposes. Starting from attack prevention, we'll see how we can reduce the attack surface in our environment to begin with. We'll see how we can detect various attacks which might be performing reconnaissance or lateral movement activities in our environment. And finally, we'll see how they can be very helpful for attack investigation as well. So very brief overview of Bloodhound. So Bloodhound was a tool which was originally created for attackers, but it can be very useful for defenders as well. And what it does is it constructs a graph which shows path which would lead from less privileged domain accounts to domain admins. So it starts by scanning the environment to gather as much information as possible to construct the graph. So that information includes local administrators and domain computers, domain group memberships, active sessions on the machines, access control lists, and a few more. And then it uses all that information in order to construct that graph which reveals paths that lead from less privileged domain accounts to domain admins. So if you're not familiar with this tool, I definitely recommend that you check it out and see all the features that it has. Another cool tool is GoFetch. What GoFetch does is it takes as an input a path generated by Bloodhound, and it automates the entire lateral movement process. So it moves from one node to the next, extracting the credentials of the next user, and so on until reaching the final node of the path, where it extracts the credentials of the domain admin and returns them to the attacker. So as you can see, once you have the entire process automated, attackers don't need to necessarily have the shortest path possible. Any path which would lead them to domain admin credentials is good enough. A short comparison between what attackers are doing today versus what defenders can be doing. So when attackers are scanning the network to gather the information, they're using limited privileges. They're using that initial account that they were able to compromise, since the entire purpose is to find a path that would lead them to a high privileged account. Defenders, however, can use any permissions that they want. Now, as a result, attackers have limited access to network resources. So this is something that depends on the configuration and hardening of the environment, since a lot of the data gathering methods require that you have administrative privileges on the target machine. So attackers would not be able to retrieve the information from all the computers. Again, defenders can access any resources that they want. Now, even though attackers have limited access, they're still able to construct a graph based on the information that they were able to retrieve. So that graph would be a partial graph. Defenders, however, can create full graphs which contains any data and network resources that they want. Even though attackers are only working with a partial graph, we just saw with Bloodhound how they can use that graph to gain very valuable insights into our environment and find complex attack paths which would lead them to compromise one of our domain administrators. Well, if attackers are using those limited permissions and data sources and are still able to leverage graphs to their benefit, the question is, what can we as defenders do with our unlimited permissions and data sources and use graphs to defend our environment? So this is exactly what I'll be covering in this session today. So how can we use graphs? Well, first of all, we'll see how we can use them to prevent attacks. We'll see how we can reduce the attack surface, how we can detect the most vulnerable nodes that we have in our environment, which can be either users and computers, and then we'll see how we can disconnect them from the attack path. Next, we'll see how we can use them for attack detection, see how to study login patterns of users and detect anomalies which might indicate reconnaissance or lateral movement activities. And finally, very briefly, we'll see how they can help us with attack investigation as well. We'll see how it can help us gain insights into the attack path, maybe understand what the attack source was, and even find additional accounts which may have been compromised during the attack. Right, before diving into every one of the stages that we just seen, let's see which data sources we'll be using. First thing that we need are the domain group memberships. We need to understand who are the high privileged accounts in our environment. Those are the accounts that are members of those high privileged built-in groups in Active Directory. Then we need to get the local group memberships on the domain computers in order to understand who has administrative privileges on every domain machine. And last and most important piece of the puzzle would be the existing credentials on every domain machine. So when I say credentials, I mean either the NTLM hash of the user or the Kerberos ticket. As defenders, we can get that information either from login events, which are usually collected to a SIEM in most environments, or from network traffic that comes to the domain controller. Now, for most organizations, it would be probably easier to use login events. However, I already had the Kerberos traffic parsed, so I used the combination of the two. So what I did is, in order to cover the Kerberos authentications, I looked into successful AS and TGS requests to the domain controller. So if there was a computer from which there was a successful AS or TGS request, it means that that computer now holds the credentials of the user. So that covers Kerberos authentications. Since the NTLM traffic is encrypted, I used a dedicated event which can be located on the domain controller, which states both the source computer, the target computer, and also the authenticated user. So by using the domain controller as the main source of information, I was able to map all the credentials that are present on the environment. The good thing about this is that we don't need to query all the machines to get the active sessions all the time, since it's something that is constantly changing, and we're also not creating any additional load on our network. We're simply using the domain controller in order to map all the credentials. All right, now we know which data sources we're using. Let's see how we can use this data. Let's start with attack prevention. So here our goal would be to reduce the attack surface in the environment. We'll see how we can discover the most vulnerable nodes that we have in our network, and then we'll see different ways in which we can disconnect them from as many attack paths as we can. The biggest problem with this approach is that computing all the attack path is a hard task. So if you have a large environment, it will require a lot of running time, resources, and also the attack graph is constantly changing. You have constantly new sessions added or removed from the environment. So the solution would be that we would not be computing the entire attack graph at any stage. We'll only be computing the last layers on the graph. And we'll try to disconnect one of the last edges in those layers. Let's see what I mean by that. Here you can see an example of a graph generated by Bloodhound. You can see different paths which lead from less privileged domain accounts on the left to domain admins on the right. Now, there can be different types of paths. However, most of them would end in a similar pattern. The most common ending of the path would be that you would have a less privileged domain account which has administrative privileges on a machine with a session of a domain admin. In that case, if that less privileged domain account is compromised, it can be used to connect to that vulnerable machine and extract the credentials of the domain administrator. So what we'll try to do is we'll focus on the last part of the graph, only on the last layers, and we'll try to disconnect as many edges as we can that intersect with one of the vertical red lines. So notice that by removing those edges, we'll also be affecting paths of longer length as well, since those would eventually merge into one of the shortest paths. Okay, so our goal is to find the nodes that are part of the most attack path. So let's see a definition. A vulnerable node is a node which has a high probability of being compromised during an attack, and it can be either a computer or a user node. A vulnerable computer is a computer which has a session of at least one high privileged account, and it has many low privileged accounts that have local admin privileges at this machine. So this means that if any one of those low privileged accounts is compromised, it can be used to connect to the vulnerable machine and extract the credentials of the domain admin. So if a computer has more administrative sessions and more low privileged accounts that have local admin privileges, we would consider the computer to be more vulnerable. Second type of vulnerable node is a user node. So this is a node that represents a user that has high privileges in the environment, and it has a session on at least one vulnerable computer. So if a user has more sessions on more vulnerable computers, we'll consider the user as more vulnerable in the environment. Something which is important to state is that the status of a node can change over time. So if a node is considered to be vulnerable today, it will not be necessarily be considered vulnerable tomorrow as well. So this is something which depends on the user behavior. Every day a user connects to different computers, and also on computer configuration. So a user can constantly add or remove local admins from the machine. So in order to find the nodes that pose the largest risk in our environment, we need to track the status of the nodes over time. So since we're collecting the sessions and we know the local admins on the computer, we can compute what percentage of the time is the node actually considered vulnerable. That would allow us to detect whether we're dealing with a constant issue in the environment. This node is constantly part of many attack paths in the attack graph, or it's just a one-time occurrence that we might not need to do anything with. So by computing this and adding the criteria from the previous slide, we can create a ranking of the nodes by vulnerabilities to detect which are the most problematic user and computer nodes in our environment. Once we found those, we need to secure them somehow. How can we secure those nodes? Well, we can either use deception, we can plant traps in our environment and hope that the attacker would fall into one of those. So if you want to hear more about this, I recommend that you check out Tom Sella's talk from DEF CON last year, where he explained this. Basically, what they do is they create new attack path and hope that the attacker would choose one of those, and then they'll be able to detect him. Another thing that we can do is simply disconnect the vulnerable nodes from the attack graph. So in both methods, we are changing the attack graph. In one of them, we're simply adding new attack path, and in the second one, we're removing existing path. So I'll be focusing on the next method in the next slide. All right, so now that we found the most vulnerable nodes, the question is, how can we disconnect them from the attack graph? Well, first thing that we can do is perform configuration changes on the vulnerable computers. So we need to examine the local admins on those vulnerable computers and their logon patterns and remove any redundant members. So this solution would be most common for scenarios with vulnerable machines that have constantly many high privilege sessions, but also many inactive local admins. So this shows us that maybe that is the misconfiguration and that local admin should not be present there. So this is a pretty simple change, and remember that every time you have a less privileged domain account that has local admin privileges on a vulnerable machine, you are adding additional attack path in the underlying graph. Now, second thing that we can do is both the easiest and the hardest solution. So it's easiest because it doesn't require any extreme changes to the environment. However, it does deal with human behavior, which might be a bit trickier to change. So this one has to do with what our admins do in the environment when they're connecting to the vulnerable machines. First thing that we would like them to do is to do it by using a network logon and not, for example, an interactive logon, in order to not expose the credentials on the vulnerable machine. That way, the credentials would not be stored on the target machine. Another thing is simply log on to the vulnerable machine by using a less privileged domain account. There are many other local admins there. Perhaps another one can be used to connect to the computer. Also, when connecting by using remote desktop, use remote credential guard. Again, in that way, the credentials of that high privileged account would not be stored on the target computer. Well, as I said, this might be a bit trickier to implement. However, if we create a ranking which shows us which users are the most problematic ones in the environment, this is something that might inspire a change for those problematic admins. Now, last one is more of a side note, which is mostly relevant for security solutions that have admin privileges on the machine. And what they can do is monitor the sessions on the vulnerable computer and disconnect any inactive sessions of high privileged accounts in order to remove them from the logon session and delete it from the computer's memory. Now, this would be a bit trickier to implement. It requires a bit more work, but the first two are actually very easy to implement. You can do it in any environment. And just by implementing those first two, you will be removing the vast majority of the attack path in the underlying graph. So I suggest that you try to implement as many of those as possible, especially for the most vulnerable nodes that you find. Now, we know that no matter how much we try to reduce the attack surface, we will not be able to remove it entirely. We'll still have high privileged accounts logging into computers that they shouldn't be logging into, or we'll have misconfiguration where a user adds local admin to a vulnerable machine that should have been present there. The question is, what can we do with the remaining attack path? Well, we can hope to detect them. First, let's begin with a few definitions before seeing the detection itself. So first we have a logon graph. So a logon graph is a graph which consists of vertices, which represent the domain computers, and the edges represent the session between those computers. So every time a user connects from source computer to a target computer, we would add a corresponding directed edge in the graph and add a label to the edge representing the user which made that connection. For example, here you can see that user 1 connected from computer 1 to computer 2, and then from computer 2 to computer 3. Okay, next and last definition is a weighted logon graph. So this is the same as the previous graph with an additional parameter on the edge. We're adding a weight to every edge in the graph. And that edge and that weight represents the probability of that user performing that connection. So we still don't know how we compute this probability. This is just a definition. For example, here you can see that the probability of user 1 connecting from computer 1 to computer 2 is pretty high. It's 0.9. However, the probability of the same user connecting from computer 2 to computer 3 is pretty low. It's just 0.05. Okay, so this is just an example. Let's see how those definitions have anything to do with detecting an attack. All right, so first thing that we need to do is to compute a weighted logon graph. So this is something which would be constructed based on the logon activities of the users in our environment during some learning period. So we'll have a month or 2 months in which we study the behavior of all the users, and then we compute the weight of every edge based on the activities of that users between the two computers. Meaning, if a user frequently connects from one computer to the other, the corresponding edge would get a high probability, and if there's a connection that the user rarely makes or he never connected to the machine, then the corresponding edge would be given a low or a 0 probability. Second thing we need is the daily logon graph. So this is something that is constructed based on the logon activities of all the users on a given day after the learning period. So first stage that we do is we take all the logon activities during that day and construct a regular logon graph. So every time a user connects to a machine, we add a corresponding edge in the graph. In the second stage, we will remove all the edges which were assigned a high weight in the weighted graph that we computed in the previous stage. Basically, we want to remove all the edges that we expect to see on a given day and only be left with the edges that are less likely to appear in our environment. And on that graph, we'll try to detect anomalies which might indicate that an attack might be going on. Right, then, as I said, we'll try to detect anomalies based on that graph. So which structures should we be looking for in that graph? First interesting structure is a star structure. So that would be a computer with many outgoing edges to other computers. All right, so this is something that might indicate reconnaissance activities, an attacker that is scanning the network, trying to access to as many computers as possible and gather as much information from other domain machines. For example, if you run Bloodhound, this is the structure that you'll expect to see in the graph. So in that case, all the edges would be assigned a label that correspond to the same user. Also, it can be a main attack machine that the attacker is using to connect to more domain computers, extract more credentials, and use them to connect to other machines. Now, in that case, every edge might get a user which might get a label which represents a different user. Next interesting structures that we'll search for are suspicious chains. So those are consecutive edges which were assigned a low probability. So for example, this might indicate lateral movement activities going on in our environment, and if you run GoFetch, this is the structure that you'll expect to see in the graph. Or it can be also a combination of the two. It can be an attacker that started with reconnaissance and then moving on to perform lateral movement activities from one of the computers. All right, so that was a lot of theoretical talk. Let's see an example from a real environment. So here you can see the daily logon graph that I got from a real environment. Those are only the edges that happened during a day that were assigned a low probability. And as you can see, there's too much data here. It's hard to find anomalies based on this graph, and we need to find a way to filter out the benign activities. Now let's see different ways in which we can do this. First thing that we can do is remove connected components that consist of only 2 nodes. So those would be the cases where we just have 2 nodes connected by a single edge without any additional connection. So it's very common for a user to connect to at least 1 new resource on a given day, so that's not very interesting. However, as you can see, we still have too much data and we need to keep filtering it out. Next thing that I did is I decided to use different features for every structure that I was looking for. So here I'll show you how I was able to find the suspicious chain in the environment. And in order to do that, I removed all the star structures that were not leading to any lateral movement activity. Again, as you can see, we still need to keep filtering the data. So let's see some more ways in which we can do this. So some more things that I did is take into account new users and computers which are added to the environment. Also, take a look at the computer and resource popularity, meaning how many users connect to the computer on a given day, and are those high-privileged users or not. Also, I took into account peers' behavior. So peers are users that have similar permissions and access similar resources. So if a user accesses a resource whose peers constantly access as well, it would not be considered as suspicious. So as you can see, when using those features, I was able to get a graph which looks a lot better. However, it's still not good enough since we can't start investigating every edge here. So since we're looking for suspicious chains, those are the ones that might represent a lateral movement activity, this is the last feature that really sealed the deal. So only considered connection when the user that performs the connection is a local admin on the target computer. This would be usually the case when we're talking about lateral movement activities. And as you can see, the data looks a lot better. We only have 2 subgraphs left. So the one on the top is benign, and it's not a suspicious chain, simply 2 computers connecting to the same one. So that could be easily filtered out. And the second one is a chain, a suspicious chain, which consists of 2 edges. And this was actually a lateral movement activity which was performed in the environment as part of a testing scenario. And we found a credentials dumping tool on the computer in the middle. So that was pretty cool. So in a very similar way, you can either use all the features, part of them, add some new ones, and also detect suspicious star structures in the environment as well. So what are the pros and cons of this approach? First of all, some of the pros. In order to fully avoid detection, attackers need to be aware of all the behavior of all the entities in the environment in order to not generate those edges which would be assigned a low probability. So this is pretty hard for an attacker. Also, it allows us to detect paths which involve multiple users, either in the star structures or in the chain structures. It can help us detect both outsider and insider threats. So it can be a user that starts accessing resources that he shouldn't be accessing. And last thing is that it can be incorporated with data that we have from the endpoint in order to strengthen our certainty in the signal and understand whether we are dealing with a benign activity or an actual attack. So we can take a look at what was going on in that source of the star structure or any machine in the suspicious chain to understand what exactly happened. Some of the cons, first of all, if the attacker responds to an entity's usual behavior, it would be harder to detect since we are relying on the fact that we would have edges that would be assigned a low probability. Second is regarding the weight threshold, which edges do we want to keep in our daily logon graph. So if we set it to be too high, we might get more false positives. If we set it too low, we might miss real attacks. So we need to find the ideal value here for your environment. Last thing is that it's harder to detect scattered attacks, cases in which an attacker connects from one computer to another by using one user, then connecting from a completely unrelated machine to another computer by using another user. So those are less common, but they're still possible and we need to be aware of those. Well, if we weren't able to detect an attack by using this method, no method can detect everything, what can we do? Well, we can always use graphs to help us investigate what happened. So just very briefly, what we can do is take all the known compromised machines and users and construct a logon graph based on those entities. So that can help us understand what was the attack path that the attacker took, maybe discover the source of the attack, and even discover additional accounts which may have been compromised during the attack, since we know which users were logged on to every computer at that time. All right, let's see some of the conclusions. We know that attackers have access to limited data sources. However, they're still able to leverage graphs and create a partial graph, which would help them to gain very valuable insights into our environment and help them find a path that would allow them to compromise a high-privileged account. So even though they're working with limited data and permissions, they're still able to target those domain administrative accounts in our environment. As we've seen, however, defenders have access to unlimited data sources. So we have so much more data, and we need to use it accordingly. We saw how this data can be used to create much more informative graphs that can help us in attack prevention. We saw how we can detect the most vulnerable nodes that we have in our environment and disconnect them from the attack graph. We saw how it can help us for detecting an attack which might be performing reconnaissance or lateral movement activities. And finally, we saw how they can help us for investigating an attack. So hopefully you can start looking into how you can incorporate some of those ideas in your environment. Thank you.